Welcome, Algebra 2 Honors. We are graphing today. We're learning a new parent graph. This one is called graphing cube root functions. Last class we learned square root functions. Now today we have an index of a 3, so we're taking the cube root, okay? All right, before we transform this, we need to know what that parent function looks like, okay, that parent graph. So make a t-table here, all right? If we plug in x values and then we get the y values. Now here's the thing. Remember on the square root graph, f of x equals the square root of x, we had restrictions on the domain, restrictions on what we could plug in and take a square root of. Okay, with the cube root, we don't have any restrictions because we can take the cube root of a negative number. So we can plug anything in here, and with that, my domain is going to be all real numbers. So I know it's easier to see domain from a graph, but again, there are no restrictions. We can have a negative inside the radical if we're taking the cube root. So keep that in mind as we plug in here. Okay, we've plugged some values into our t-table for x. Again, we can take a cube root of a negative number. So the cube root of -8, or what number times itself 3 times equals -8, is -2. So if we plot these points on our graph, you'll notice that we have kind of some symmetry here. Okay. So when you draw this, it's kind of like a square root graph on the right-hand side, but then it also takes a turn and then continues on the left-hand side. So we want to make like a smooth, nice S shape here. One thing to point out in the middle here, this is where it takes that turn. This is called your point of inflection, okay? So that's kind of like your vertex, your starting point on other graphs. It's just not a vertex now. It's the point where it kind of takes that turn. All right, domain. Again, we talked about what we can plug in for x. We can plug in anything, so there's no restrictions. This graph goes to the left forever, and it also goes to the right forever. So we have all real numbers or from -infinity to +infinity. And for range, we can have any output values as well. So this graph goes down forever and up forever. So same thing, we have all real numbers or from -infinity to +infinity. End behavior as x goes to infinity. So as this graph goes to the right, the y values are approaching infinity. Okay, those are going up forever. Again, this graph kind of flattens out, but it will continue to go up and up and up, just a lot slower than it goes to the right. As x approaches -infinity, this function is going to also approach -infinity because it's going slightly down forever and ever and ever. Okay. All right, with every other graph we've done, we can transform this graph, a couple different things. Inside that function, that h value is horizontal movement, but always backwards. That k value outside of the function, outside of that radical, is always up and down vertical. And that a value out front, a couple things. First of all, if it's negative, we're reflecting across the x-axis, and then stretch or compression based on if it's greater than 1 or less than 1. All right, with that, we also have a b value, okay? We haven't done the b value as much. This one's a little harder, okay? Again, think of when it's inside the function, it's affecting the x values, okay? So everything that's being done is going to affect the x values. So if we have a negative in there, a negative b value, it's reflecting across the y-axis, okay? Because any point is now going to have a different x value to it, okay? So the positive x will now become negative x, okay? We also have stretch or compression. Here's the thing, with that b value, it's backwards, okay? So if you have like a, let's say 3 times x minus 3, and this is a cube root, if you have a b value of a 3, okay, this is horizontal and it's going to be a compression. Okay? So you have to think of, if this is 3, that means the x is now going to have to be a third as big as it was before to keep that function the same. So let's practice that. Those are a little trickier. All right, here's our function that we're going to graph. We have 3 different transformations happening to it. Okay, we're going to make a t-table to kind of see where this is. But before we do that, we want to find that point of inflection. X plus 4 means that it's moved 4 to the left, and then plus 3 is 3 up. So we're going to find that point at negative 1, 2, 3, 4, up 3. All right, there's my point of inflection. Okay, from here, I can know kind of which values to choose. So I'm going to make a t-table, plug in some x values, and I'm going to plug them into this function, which is a cube root of 2 times x plus 4 plus 3. And now I need to pick some values that fit nicely and give me a nice cube root. So I'm looking for anything that will give me a 1, 8, a 0 in here. Okay, let's choose some values. All right, I've picked 2 values in here that are going to give me perfect cubes inside the radical. So if I plug in, again, think if I want a 1 inside of this radical, it's being multiplied by 2. That means that this chunk here is going to have to equal to 0.5. So if I plug in negative 3.5 for x, I get the cube root of 1 plus 3, which is just going to give me 4. And again, if I plug in 0 for x, then I'm going to have the cube root of 8, which is another perfect cube, so I get 5. All right, these are a couple points on my graph. Let's find a couple more. All right, the nice thing about this is that because of that symmetry, from that purple point, if we want 0.5 over to the right, do 0.5 over to the left. So we're going to plug in negative 4.5 for x, and that's going to give me the cube root of negative 1 plus 3, so I get 2. All right, and I went 4 over to the right for to find a perfect cube, so I'm going to go 4 over to the left and plug in negative 8 for x, and if I do that, I get the cube root of negative 8, which is negative 2 plus 3 equals 1. All right, let's plot these points here. There's a point, and then negative. There we go. So here's my graph. We just need to kind of connect the dots, make sure it's a nice, pretty, smooth graph here. There we go on the right, and then that point of inflection is where it's going to take its turn. Okay, so there's my graph. Technically, for describing the transformations here, again, this is horizontal shift 4 units left, vertical shift 3 units up, and this 2 here, again, it's inside with the x, so it affects horizontal, and it's a value of 2, so this is going to be a compression by a factor of 1/2. Okay, again, that b value is backwards. All right, let's take a look at another one here. We have a couple transformations. This one has a negative, so this is going to reflect over the x-axis. Okay, vertical stretch of 3 units, 1 unit to the right and down 2 units. So let's start with that point of inflection, moving over 1, down 2. We're going to make a t-table, find some other points, and plot those. All right, these are the values I chose. These are ones that are going to give me perfect cubes inside. So I'm looking for what am I going to have to give me 1 in here. So if I plug in 2, I'd have a perfect cube. If I plug in 9, I would have the cube root of 8. If I plug in 0, I would have the cube root of negative 1. And if I plug in negative 7, I would have the cube root of negative 8. So those are going to give me the perfect cubes. All right, here's my plots, my points plotted. Again, you can see that there's the reflection over the x-axis because now my end behavior is going up on the left and down on the right. And then if you picture that vertical stretch, each of these points are kind of being pulled up and down from where they normally would be. Okay, so there's the best of my graph, the best I can do with what I have. All right, again, domain for any cube root graph. There's no restrictions on what I can plug in for x. So I have all real numbers or negative infinity to positive infinity. And because of that, there's going to be no restrictions on my range as well. So negative infinity, positive infinity. All right, we have another graph here. We have x minus 3. Again, let's start with that point of inflection. We're going 3 units to the right and 5 units up. There's that point. Let's kind of just describe what else is happening. I have a b value inside here of 1/2. So remember, this is always horizontal because it's inside, it's affecting my x values, and it's always backwards. So if it's less than 1, this is going to be a stretch by a factor of 2. Okay. Again, think of if this is 1/2, my x value is going to have to be twice as big to kind of make up for that 1/2 to keep my function the same. Okay. Again, that b value is just a little tricky. Okay, let's find some points here for my t-table. All right, here's the points I chose. Again, we have to kind of think if whatever we're plugging in for x, we're subtracting 3 and then multiplying by 1/2. And we want to end up with the value of 1 and the value of 8 here. So if we plug in 5, 5 minus 3 is 2, times 1/2 is 1. Okay, so think of it that way. Plug in values, kind of play around, work backwards to see what's going to give me a perfect cube. I take it back. I'm going to need a 19 in here so that I have 1/2 times 19 minus 3 is 16. So that way it's going to give me an 8 in here. Okay, so plus 5. So 16 times 1/2 is 8. Cube root of 8 is 2. Plus that 5 is going to give me 7. Okay, plug in 1. Again, we get 0.5 times 1 minus 3 is negative 2. Plus 5, that gives me my perfect cube in there. Okay, here's my updated points. We found some better perfect cubes. So 5, 6, we got some, again, with that stretch. Try and keep them all in the graph. Sometimes we have to get some bigger numbers that go pretty far out. So 5, 6. 19, 7. So we're going to be off the graph here, but you can kind of imagine. It's over there. Then we have 1, 4. Negative 13, again off the graph 3. So again, because of that horizontal stretch, everything's kind of pulled left and right. But here's my graph. It's kind of, and then again, at that point of inflection, it's going to take the turn and go that way. All right. Okay, now we did some graphing. We're going to work backwards, and given a graph, we're going to write the function. Okay, a couple things we need to notice. Basically, it gives you that point of inflection. We can kind of see where that graph is taking its turn. So that's going to be my h and k value to plug in. And I can take any other point on this graph and use it as my x, y value. All right. When we plug these 4 values in, then basically all we need to do is find that a value to see if there's a horizontal stretch or compression. So let's find these points for hk. This graph is kind of scaled weird, so be careful with that. We have 1, 7. So I'm going to use that for my hk. Over here for xy, I have 9, 11. All right, so for my function, I'm going to plug in y. 11 for y is equal to my a value times the cube root of x, which is 9 minus 1 minus my h, plus my k value of 7. Okay, so the only variable I have now is a. I just need to evaluate this and solve for that. So I get 11 is equal to a times the cube root of 8 plus 7. 11 equals a times 2 plus 7. All right, let's subtract 7 from both sides here. We get 4 is equal to 2a, and if we divide by 2, we get a equals 2. So this graph has a vertical stretch. When we write our function, we're going to be left with g of x is equal to 2 times the cube root of x minus 1 plus 7, and all we do is just fill in that point of inflection, the hk value. All right, there's my function written from the graph. Okay, we have another one here that we're going to write the function. I see a reflection in here, so let's see how that works, okay? Again, find that point of inflection. It's right where it's starting to kind of go down and then back the other way. So we have to choose the right point. So I have, let's see, 2, negative 6. That's, again, going to be my hk value. And then let's pick any other point over here. We have, let's see, 10, negative 10 for my xy value. Okay. Again, we're using this function here, a cube root of x minus h plus k. We can fill in h and k with what we know. 2, negative 6, so minus 6 at the end. Again, make sure that's always outside of the radical. And then we can always just plug in x and y as well. So For my g of x, that's my y value, I'm plugging in -10. And for my x value, I'm plugging in +10. That leaves me with just the a value, which is that vertical stretch or compression, to figure out. All right, -10 is equal to a times the cube root of 8 minus 6. -10 is equal to a, the cube root of 8 is 2, minus 6. Add 6 to both sides here. We get -4 is equal to 2a. A is equal to -2. Just double check that, make sure. Again, because we're going up on the left with the end behavior, there is going to be a negative, so that value turned out for us. Our function, therefore, is g of x equals -2 times the cube root of x minus 2 minus 6. Okay, again, this is +2, so make sure it's x minus 2 in there because the minus sign is already there, and there's our function for that one as well. All right, here we are modeling with cube root functions. We have some beautiful elephants there, and the shoulder height here for a particular elephant is modeled by the function h of t equals 62.1 times the cube root of t plus 76. So the height is given as a function of the age of the elephant. Here's our graph down here. It's asking us a couple things. First of all, evaluate the rate of change over the certain intervals. So we need to plug in these values of 0 years old, 20 years old, 40 years old, and 60 years old into this function for the elephants so that we can see how high their shoulder height is, okay? And then we're going to kind of determine what that average rate of change means, okay? Okay, filling in my chart, all I did was plug in for t here. Just a heads up, if you want to take a cube root on your calculator, depending which one you have, if you have a TI-83, you're going to hit the math button. And I think this works for any TI-81s, 84s. Hit the math button, and then you're going to go down to the button that looks like this. It has a 3, and then it has a radical, and it has kind of a parentheses. Okay, so that's how you take a cube root if you're kind of unsure on your calculator. If you're doing this on a TI-30, I believe, you're going to have to press the 3 button first, and then the second, and then the caret button, and that's going to give you a little button that I think has an X there. So you put the index in and then that, okay? All right, so just based off of our graph and just based off this data here, I can see that from 0 to 20 years old, this elephant is growing really, really tall. It's going from 76 centimeter shoulder height to 244. The next 20 years, it's gaining only 44, and so the growth is slowing down. So let's find that average rate of change, okay? Again, average rate of change we're going to do for certain intervals. So from 0 to 20 years old, average rate of change is change in y, so change in height over change in age. All right, so from 0 to 20 years old, our average rate of change was 8.44. From 40 to 60 years old, again, change in y, so 319.1 minus 288.4 over my x, so 60 minus 40, we have 1.54. All right, so what is happening to the average rate of change as the t-values increase? Let's use in the context of the problem. So what I wrote was, first of all, the shoulder height per year of age. That's what the rate of change represents. Now, in the context of the problem, the shoulder height per year of age decreases as the elephant gets older, because you could see the interval of 40 to 60 years old has a lower rate of change than the interval of the first 20 years of their life, okay? So the shoulder height per year of age decreases as the elephant gets older. Basically, they're growing less fast than they were when they were younger. All right, come back to the Google Meet. Good job. Let me know if you have any questions.